Alright, we're going to knock out a couple more quick molarity examples, and these are fairly straightforward. I broke this piece of paper up into this way intentionally so that we could deal with part B of each of these separately. For right now, we're just going to approach this blind and say, alright, we're looking for brackets. Brackets implies concentration, specifically it implies a molarity. If you don't know what to do, start out by writing the equation. We happen to know molarity is supposed to be moles of the solute over the volume in liters of the solution. So we write our equation and use it as a checklist. Do I know the molarity? No, I want to find it. Do I know the moles of the solute? No, but I know a mass, so I'm going to be able to get it. Do I know volume in liters of the solution? Well, I know milliliters, so I effectively know it. So once again, our strategy, write the equation and use it as a checklist. Even if we weren't told we were looking for a molarity, that's all we could get. Now, in order to plug in to solve for that molarity, we're going to need to get the moles right there, and we're going to need to get the volume. And I think the volume is going to be a lot faster to grab. 511 milliliters of solution, right? So when you're looking at this, sometimes it's easy to be distracted and say, 500 milliliters of water. Well, our equation doesn't say volume of solvent. It doesn't say volume of water. It says volume of the solution. So this is super important when we plug it in right there. And I do want to point something out. Adding salt, table salt, to water will change the volume. It doesn't change it in any super obvious, predictable way, but it's going to make the volume go up. That salt does take up some space. It doesn't take up as much space as it would if it remained solid, but we do have our volume going up when we add that. So once again, this part right here is a trap. You don't need it because you need solution for that calculation. And in this particular case, that's 0.511 liters. All right. When we do this calculation then, it's 0.511 liters total solution volume. Now to get moles of our solute, we have a mass. We can get moles as mass over molar mass. In order to do that, we need to know the molar mass. Luckily, I'm sure you're quite proficient at calculating molar mass at this point. If we have our NaCl, it has a molar mass of 58.44 grams per mole. All right, NaCl, 1 sodium, 22.99, chlorine, 35.45. Add them together, you get that. We know that moles is the mass over the molar mass, The mass is our 25.0 grams, and the molar mass is our 58.44 grams per mole. Grams canceled, moles is in the denominator of the denominator, and we end up with 0.427 moles. And that is the number we will be plugging in for our numerator. All of my highlighters have disappeared. So this is 0.427 moles. That is going to be my numerator right there. Punch that into the calculator. We end up with 0.837 molar NaCl. Let's write that down. 0.837 molar NaCl is our concentration of NaCl, and that is our answer to part A. Other than a few intricacies, these molarity calculations are all the same. In number 3, I followed that set of instructions that I described in the previous video, where we had said dissolve some amount of solute in your solvent, then dilute to a total solution volume using your solvent. Well, there is that exact formula right there. That's how instructions look for preparing a molarity. Following the same procedure we have used and we will use for most of the calculation problems, write the equation, use it as a checklist. I know molarity is supposed to be moles of the solute over volume in liters of the solution. And I didn't mention it on the previous problem, but if you're looking for ways to spot what is the solute, what is the solvent, well, this K3PO4 is dissolved in water. So that water has to be our solvent. Similarly up here, NaCl is added to the water, right? So our water ends up being our solvent there as well. and by process of elimination that leaves the K3PO4 potassium tripotassium phosphate as our solute. Write the equation, use it as a checklist. Do I know the molarity? No. Do I know moles of solute? I can get it. Do I know volume in liters of solution? I can get it. So I can find molarity, and not coincidentally, that's what I need to find. A piece of information that we will need, I calculated it in advance, the molar mass of potassium phosphate is 212.3 grams per mole. And if that weren't given, you would just add up 3 potassiums, 1 phosphorus, and 4 oxygens. Also, I guess we should take care of this right here. This is 0.250 liters. Unlike this problem up here, where we were given an amount of the solvent and then looked at the amount of the solution, in this problem right here, we have a total solution volume of 0.250. So that's the number we're going to end up using. In this case, moles of our solute we're going to have to calculate, and we know that your moles is going to be your mass over the molar mass. We're given 44.4 grams, and it is 212.3 grams per mole. So our moles, we end up with 0.209 moles. That is the number I'm going to put here, 0.209 moles. Now, I've learned a fatal flaw of these new pens. They seem to blur very easily from the highlighters. Our volume in liters of the solution, we wrote it right here as 0.250 liters. 0.250 liters. And we'll see if we can say where that came from. Now, when you do this, I intentionally set it up so that we would end up with a shockingly familiar number, and that shockingly familiar number in this case is 0.837 molar. All right, so that is our answer to part A for number 3. And there's a few things I want to point out. It's not super important, but we had different masses, but we got the same concentration. It's not just because we had different volumes, because we did, but we also had different molar masses, all right? So it would be coincidental that these two numbers ended up the same, except I prearranged the numbers so they would end up the same when we're looking at this part B, the concentration of ions. So don't be fooled by the fact that these two are the same. That's an incredibly improbable situation for things that have different masses, different molar masses, and different volumes. So let's address part B now, the concentration of ions. B, the concentration of ions. And I'm going to do this the long way 1.5 times, and then I'm never going to do it the long way again. We are looking at these aqueous species, and in both of these cases we're going to assume that we have strong electrolytes. And if you're not familiar with that terminology, strong electrolyte just means it dissociates, and I'll put it in quotes, completely. We know how to write dissociation equations, so in this particular case right here, if we're dissociating NaCl, we'd write that as sodium ions and chloride ions. And we've written that before in our double replacement reactions when we're looking at complete and net ionic equations. You may remember me saying as well that there's no salt in salt water because NaCl dissociates to sodium ions and chloride ions. This number here I'm just going to write in so we can see it. We have 0.837 molar NaCl, and I want to get the concentration of the sodium ions that it produces and the concentration of the chloride ions that it produces. I'm going to show you the long way right here, and then I'm going to do it the short way, and then I'm going to do it the short way, and then I'm going to do it the long way more or less, just so you can see how that relationship works out. Spoiler alert, 0.837 and 0.837 for the sodium ions and chloride ions. I'm going to do some dimensional analysis over here. Start with what you're given. 0.837 molar NaCl. I want to find out about those ions, and I know that for every one NaCl, I've got one Na and one Cl. And my colors are kind of going out the window here. One sodium ion, and then we end up with 0.837 molar sodium ions. And one chloride ion, and we end up with 0.837 molar chloride ions. And this is our answer to part B. And I said that's the long way. I wouldn't really recommend doing that. Like, I think it's actually more work and a little less intuitive to break it up, showing the dimensional analysis of what's really going on. So what I will tend to do, and what I recommend that you do as well, is when you look at this number right here, just show your dimensional analysis in a more primitive way. I'm going to take this number and I'm going to multiply by the number of sodiums that I have. That's 1. So for every 0.837 molar sodium chlorides, I end up with 0.837 molar sodium ions. And then, I have no idea what that clumping is upstairs, if you can hear it. For every 1 NaCl, there's 1 Cl. For every 0.837 NaCls, we're going to end up with 0.837 molar Cl minus. So this and this are the same. And I would probably do it the fast way, which is take your subscripts, multiply by them, it gets you those, because that's exactly what goes on in that stoichiometry. Let's take a look at this one, and I said this one we'll do the fast way, and then we'll do the slow way. If you were to give me this problem and say, get the concentration of ions in here, well, I'm going to declare this is going to dissociate. One small skill you need to pay attention to is that phosphate is a polyatomic ion, and I have one of it. All right, so this will not break down into phosphorus and oxygens, and we know that when we looked at double replacement reactions and solubility and things like that. So this number here and this number here are the numbers of interest to me. I'm going to multiply by, for every one of these, there's 3 of these. So that's what stoichiometry says, that stoichiometry is just ratios. So I'm going to multiply by 3. And for every one of these potassium phosphates, there's 1 phosphate, and so I'm going to multiply by 1. And that gives me 0.837 molar phosphate ions and 2.51 molar potassium ions. And that would be our answer to part B right there. So every single time I'm asked to come up with a concentration of ions given a concentration of some salt, this is the cheapest and dirtiest work I can use to do this dimensional analysis. And I said I would set this one up that way. In our dissociation here, we know that K3PO4 is going to give us 3 potassium ions and 1 phosphate ion. And when we set up our dimensional analysis, we're starting with 0.837 molar K3PO4. And I know that for every 1 K3PO4, we have 3 potassium ions. And so 0.837 times 3 divided by 1 is 2.51 molar potassium ions. And then for every 1 K3PO4, I've got 1 phosphate. And so we end up with 0.837 molar phosphate. And unsurprisingly, those answers are the same. Now, to let you in on what was going on far behind the scenes, I made sure that this number and this number would end up the same so that you could see that these numbers can be drastically different. 0.837 molar NaCl has 0.837 molar sodium ions and 0.837 molar chloride ions, because this all dissociates. In this one here, 0.837 molar potassium phosphate has 2.51 molar potassium ions, because it's 3 times that. There's 3 times as many. And then it has 0.837 molar phosphate ions. So even though this concentration and this concentration are the same, the total number of ions in the solution are drastically different. I think that's kind of interesting and not necessarily intuitive. This makes 2 things. This makes 3 plus 1 is 4 things. So we get a much higher concentration there.